by DJNZ DJNZ, which means it decrease the first operand is decreased by 1. If it is not a 0, jump to the target, referenced by the neighbor, Prior to the start of the loop, the register is loaded with the count for the number of the repetitions. Counter can be R0, R2, R7, or RAM location. For example, this program adds value 1 to the A 10 times. 10 times is. First, move A, $0, which means A is equal to 0. A is equal to 0. Clear A move R2, 10. Now the counter R2 is equal to 10. Next is looping. This is a neighbor. This is a neighbor. Neighbor for the looping neighbor. Here is the looping is DJNZ. Add A, .03, add 3 to ACC. DJNZ, R2 is equal to 10, decreased by 1. This is by 1. If it is not 0, jump to again. Again is a neighbor. Here is a neighbor with a 2 point. Jump to here. This is a loop. This is a loop. If other 2 is equal to 0, according to the next instruction. This is a little example for the loop. Here, I will show you how to run this loop. Last time, I have already introduced the simulation software. Here is the Protos 8, professional. We can just open this project. This is a project we built last time. We just change this.
Actually,
Okay.
in the C programming we learned, there was this loop for and while. Is it available in the assembly language?
Sorry, I cannot hear you. There's some noise in your voice.
Last week, can you hear me now, please?
Now it's clear.
Okay. Actually, in the higher languages like C programming and Python, there's a loop for and while. Is it available in the assembly language, or they don't support in the assembly language?
Don't support this language.
They don't support?
Sorry,
Hello?
can you text me with the meeting message?
Okay.
Okay. Oh, you want to use the for and while loop in the assembly language? We cannot use it. We cannot use it. This is for and while loop is used in the C language. Yeah. I don't know if you can see this code. Everyone can see the code.
Yes, Lord, I can see.
Okay. If we simulate this code, first build, if compiled successful, compiled successful, and debug, start debugging, started debugging. First, move a comma pound 0. Now a is equal to 0. We can see register. ACC is 0. ACC is 0. Next, move R2 10 10. We can see R2 is equal to 10. 0A 0A is 10 is 10. Next add A comma pound 03 03. A is equal to 0 and add 03 is equal to 03. So we can see ACC is 03 03. Next DJNZ DJNZ R2 R2 is equal to 10 and it decreased by 1. So this is now is 9 9 R2. You can see R2 is 9. R2 is 9. R2 is 9. So we can see next move. Next move. Add A 03. So now is A is 06. 0 is 6. Here we can see ACC is 6. DJNZ R2 R2 is 08 08. So jump not at 0 not at 0. So jump back to again again. So repeat repeat repeat. We can see now R2 is equal to 0. So move to the next instruction. Next instruction. So move RA, comma A, comma A. So R2 we R5 R5 is A the result saved in A E 1 E 1 E. So we can see with this simulation software we can watch the process. Watch the process. If we want to repeat the action more times, then 256 we use a loop inside a loop which is called a nested loop nested loop. Use the DJNZ, we can repeat the loop 256 256. If loop is more than 256 56, we can use a nested loop with two DJNZ two DJNZ instruction. Anyone want me to simulate this software, or we continue introduce the PPT? Anyone can hear me?
Yes, Lausi, we can hear you. Lausi, can you give us an example of the nested loop?
I want to show you the simulation. Is that okay?
Okay, Lausi, okay.
Okay. Now I simulate this is code simulate code. This code executed line by line line by line. Here first move a pound 55H. After this line is executed, we can see A is equal to 5, equal to 5. So next, move R2 to move R2 pound 70. You can see after this R3 pound we can see R3 here. R3 is A. R3 is A. After this is executed, R2 is equal to 70. R2 70. This 70 is decayed decimal. This R2 is binary. Binary. So after this line is executed, we can see R2 is equal to 46. 46. Jump to the next instruction. Is after this is executed. CPLA converts position logical position logical, which means A is gets converts the logical. A is of A as A. Here I can see This A is 55H 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 1 0 0 0 0 0 5 0 0 0 0 This is 5 H 5 H So if we use execute the CPLA, we can get 0 0 This is A H A H. So here is A. As CPLA is executed, we can get the result. This result. Next, DJNZ R2. R2. Sorry, is there any noise in the voice? This instruction R2 comma again R2 is equal to 70 70 R2 and 46H 46H. So R2 decreased by 1. You can see is 35 35 here 35. So jump back to A jump back to A. So repeat the internal loop internal loop. Repeat the internal loop until the R2 is equal to 0. R2 is equal to 0. You can see R2 is decreased by 1. Now R2 is equal to 2.
Lastly, please can you hear me? No. Please and join again.
R2 now R2 is equal to 1 is equal to 1. So after executed again, we can see R2 is equal to 0. So execute the next instruction to the next DJNZ DJNZ. So R3 is equal to 10. R3 equal to 10. So decreased by 1. It's not 0 not a 0. So jump to next jump to the next next. So now next next. This now jump to the internal loop again. generate loop again. So we can see there's two D, J, and Z. We can see after internal loop is finished, jump to the outer loop. So outer loop is going to the inner loop. After the inner loop is finished, jump to the outer loop. So until the out loop is finished, jump out to the loop, jump out from the loop. This is a nested loop. It's a this is a nested loop. Nested loop. Jump if only if a certain condition is met. If a certain condition JZ never JZ never. This is the instruction JZ JZ. Jump if A is equal to 0 to the neighbor. This is an example. Move A as 0 JZ over if A is equal to 0, jump to over jump to over This is jump to over JZ JZ. There's JZ instruction. We can JNZ JNZ. This is a JNZ JNZ. Jump if A is not a 0 it is not 0 This instruction we can remember. J is jump and not Z 0 0 jump not 0 jump jump is instruction jump instruction JNC JNC JZ judgment A judgment A judge judge A JNC judge the C judge the C jump if not 0 if not 0 which JNC NC if CY is equal to 0 jump to jump jump CY is equal to 0, which means no carry no carry, so jump jump to the neighbor If CY is equal to 0, the CPU starts the fetches and executes instruction from the address of the neighbor jump to the neighbor If CY is equal to 1, it will not jump but will execute the next instruction below JNC JNC. This is the example. Find the sum of the values 79H, 5 F5H, E2H. Put the sum in the register R0 and R5. R0 no bytes. R5 high bytes. High bytes. We can simulate this program. and OF in 0 5 H JNC N 2 JNC N2 INC R5 N2 N2 ADDA fund 0E2H JNC OER NCR5 OER OER start the debug build. There is a error. Oh, sorry. R0 debug execute this program line by line. Move A comma .0 move R5 A R5A. So now A is equal to 0, R5 is equal to 0. And A 79H. Now A is equal to 79. Here we can see here. Execute. Add A .05 F5H. F5 add 79. F1 79. So we can get the result 6E 6E 6E. JNC N2 JNC N2 So if not if NC if CY is equal to 0, so jump to R2 N2 jump to N2 here. We can check CY is equal to 0. CY is equal to 0. Here we can use this. This is calculate in your Windows systems. We can see 79 H 79 add F5 add F5 add F5 here is equal to 16E 16E. So there is a carry L is a carry. This one is a carry. This one is a carry. So carry is equal to cy is equal to 1. So if this JNC JNC, which means cy is equal to 0 to jump. Now the cy is to 1. So this after this 9 is executed, don't jump to R2, just execute this next instruction. Next instruction. INC R5, INC R5. R5 is R5. R5 is equal to 0. R5 is equal to 0. So INC R5 add 1. Add 1. So R5 is equal to 1. Add A 0 E2H E2H. A is 6E 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 add E2H E2H add E2 now is equal to 150 150. The value in the A is 50 50. So we can see this. We check this result. Yeah. Now A is 50 50. JNC JNC over JNC over JNC is cy is equal to 0 jump to the over. Now cy is equal to 1 this is 1 1. Don't jump don't jump, just execute the next instruction next instruction INC 5 INC R5 R5 is equal to 1 INC we can see R5 is equal to 2 R5 is equal to 2 the final instruction move A R0 A is to 50 50. R0 now is 50 50. This is the loop under the jump jump this is JNC JNC 8051 conditional jump instruction conditional jump conditional jump JZ if A is equal to 0 JNZ not 0 DJNZ not 0 decrement and decremented decreased by 1 is not 0 or not 0 jump jump CJNZ compare not equal jump is CJNZ not equal jump. JC JNC JB JNB JBC JBC this all is the jump for the conditional jump conditional jump instruction conditional jump instruction all conditional jumps are short jump short jump. The address of the target must within the minus 128 to plus 127 bytes of the content of the PC Why is this range? Why is this range? We can use it. I can explain it. There is a 5 bit, 5 bit, 8 bit, 8 bit. If 0, 1, 2, 3, 5, 6, this 4, 6, 7. This is for the minus and the plus. For the minus and the plus, plus and the minus. This is for the jump range. So we can see the maximum value is 7. This is 7. 1, 1, 1, 1, 1, 1, 1. Powered 2 powered 7. 2 powered 7 is equal to this 127. 127. This is a jump range. Jump range. Additional jump. Additional jump is a jump in which control is transferred unconditional to the target. LJMP. LJMP. Long jump. Long jump. 3-bit instruction. First bit is operand. Is opcode. First byte is opcode. Second and the third repeat the 6 bits target address. Represent the 6 bits target. The target is 6 bits. 6 bits. Any memory location from 0 to 55H. 055H. Short jump 2-byte instruction. First byte is opcode. Second byte is relative target address. Relative target address. Forward to plus 127 or backward to minus 128 bytes from the current PC. From the current PC. This is SJMP. SJMP. To calculate the target address of a short jump, the second byte is added to the PC of the instruction immediately below the jump. Below the jump. If the target address is more than minus 128 to plus 127 bytes from the address below the short jump instruction. The assembler will generate an error stating the jump is out of range. Out of range. Jump range. Jump range. Here is example jump. This is a opcode opcode. This is a PC this is a PC opcode. We can get the opcode after the symbol language is compiled is called. So we can see the we can't see the opcode. We can just use this example to use the jump range. Jump range. Call instruction is used to call subroutine. Subroutine. This is a call instruction. Call instruction. Subroutine are often used to perform tasks that need to be performed frequently. Frequently. If you have some function will repeat again, so you can make a subroutine and call this subroutine with the call instruction call. This makes a program more structured in addition to saving memory space. Memory space. L call, long call, and the short call absolute call, absolute call. L call 3 byte instruction just like the LJMP, LJMP. The first byte is the opcode. The second and the third byte represent the address used for the address of target subroutine. Subroutine is located anywhere within 64 KB address. A core absolute core 2 byte instruction 11 bits are used for address within 2K range 2K range. When a subroutine is called, control is transferred to that subroutine. The processor saves on the stack of the address, and the instruction immediately below the core begin to fetch instruction from the new location. After the finishing the execution of the subroutine, the instruction RET transfer control back to the corner. Control back to the corner. And this contents I have already introduced. But we don't simulate this program. So let's have a simulate about this program. ORG 0 by MOVA 1 and 55H MOV P1A LC L core delay SJMP back and RG 300H DDL1 MOV R5 and 0FFH again DJNZ R5 AGARN RET RET END RST. Okay, let's start. Oh, sorry. Oh, sorry. This is a simulate. Here I introduce the this column. This column is the PC PC count. PC count. This is code. This is code. This is error core delay. Error core delay. Here is error core delay. Here is a delay. Delay is here. Delay is here. This error SJMP back. Back. You can see back is here. From here we can see the subroutine just give the code with the neighbor. Neighbor is the subroutine name. Neighbor. After the subroutine is finished, use the code RET, which means return. So after the subroutine is finished, return back to this. Return back to this. So this is return. You can see subroutine started with the neighbor subroutine name, and with the RET. This is just give you the example for the subroutine and the error code error code. It's ORG ORG. ORG, which means set the code, it is the address ORG 00, set the code it is the address 0 we can see from here ORG 0 so the next instruction is set H0 ORG 300H so the next instruction is set it is address 0300 0300 so it's just give you an example if you want to simulate the example you can do it by yourself do it by yourself now I give you something about the structure the structure for the whole program for the microcontroller microcontroller the address from 0 the address from 0 give you a error code for the main give you error code for the main so next is error code for the instruction for the interrupt for interrupt this is for interrupt this is for the interrupt so after the interrupt call is the main program this is the main program so after the main program we write the subprogram just use the name as the neighbor and end with the RET this is subprogram 1 subprogram 2 subprogram 3 finally is the end end of the ASM end of the ASM it is common to have one main program and many subroutines that are called from the main program. This allows you to make each subprogram subroutine into a separate model. Each model can be tested separately and then brought together with the main program. In a large program, the module can be assigned to the different programmers. So use the core. We can write the different subroutines. Oh, sorry. We have the class for a long time. We can have a break, okay? Everyone,
okay.
We have a break.
Okay.
You can have a rest.
Mm-hmm.
Hello. Hello, everyone.
Hello，老师。
Yes, 老师，
let's
老师。Okay,
let's continue our class.
Yeah, 老师。
I have already introduced the program structure. If you want to write some assembly language for your program, you may refer to this structure. This structure. Next, introduce continue introduce the core instruction. Core instruction. The difference between A core and L core. The target address L core can be anywhere within the 64 KB. The target of A core must be in 2K. In 2K. The use of A core instead of L core can save a number of bytes of program or ROM space. Save a number of bytes of program ROM space. ROM space. Here is an example. ORG0, ORG0, set the address is 0. This is A core, this is A core, L core, L core. This is L core. If we want to save the storage, we can change the A core, L core to A core, L core to A core, L core to A core. CPU executing an instruction take a certain times, a certain number of clock cycle. These are referred as to a machine cycle. Machine cycle. The length of a machine cycle depends on the frequency of a crystal oscillator connected to the 8051. In original 8051, one machine cycle lasts 12 oscillator period. So we can see the machine cycle is 12 times oscillator period. See this example. Find the period of a machine cycle for the crystal frequency. The machine cycle the crystal frequency divide 12 get the machine frequency. Machine frequency. So the machine cycle we can get from here. For 8051 system, how long it takes to execute each instruction? We don't remember this result. Machine cycle for each instruction. If you want to know you can check the reference book. This is another example. Find the size of delay in the following program if the correct frequency is R. Here is the delay subroutine. We calculate the delay according to the machine cycle. Move executed in one machine cycle. DJ and Z into machine cycle. RET into machine cycle. So here we can calculate the delay time. We just calculate the how many machine cycle the subroutine will cost. So we can know the delay time. Here is a loop. This is a loop. This loop 200 loop. So 200 times 2 for one time execute time. So here is the loop machine cycle. So add this 9. Add this 9. So we get the total machine cycle. Total machine cycle times the machine time. So we can get the delay time. This is another example for calculate the delay. Here is a little different. There is no loop. This loop. There is some NOP operation. Do nothing. This operation do nothing. Just cost one machine cycle. So we can calculate the total machine cycle. Times the machine time. So we can get the delay time. Next example is the same. So I don't introduce. You can read this example by yourself. There is different.
Lofi, can you go back please again? Yeah. Oh, okay, Lofi. It's okay.
Okay. There's different microcontroller. We can get the different delay, but you need to know the machine cycle. For the microcontroller. If we know the machine cycle and we know every instruction cost the machine cycle, so we can get the total delay time. Here is some example. I don't introduce. Okay. Next, I give you some new content. Next, I introduce some instruction for the I/O port. I/O port. This is 8051 pin and diagram. We know there is a P4, P1, P2, and P3. There is four ports. Four ports in the 8051. 51. We can use the port as the I/O interface. I/O interface. Each port takes 8 pins. 8 pins. Which means 8 bits. With 8 bits. The 4-bit I/O port each use 8 pins. After all the ports upon reset are configured as input. Ready to be used as input port. If we reset the microcontroller, we can get the port used as input. Used as input. When the first zero is written to a port, it becomes an output. To reconfigure it as an input, a one must be sent to the port. To use any of these ports as an input port, it must be programmed. It can be used for input or output. Each pins must be connected external to a 10K ohm pull-up resistor. We have already introduced for the port 0. If we want to use port 0 as I/O port, we need to connect it to a pull-up resistor. 10K ohm pull-up resistor. This is due to the fact that the P0 is an open drain, unlike P1, P2, and P3. Open drain is a term used for MOS chips in the same way that open connector is used for TTL chips. So if we use P0, we need to connect the 10K ohms resistor to the P0. Just like this figure. The following code will continue send out to port 0 to alternating the value of 55H and AAH. I simulated this code for you. Okay. ACK. MOV A 55H MOV P0 A ACALL DELAY MOV A OVH MOV P0 A ACALL DELAY BACT. This is the program. We don't write the subroutine delay. Just comment. Comment this line. Comment this line. It's just for delay. So we debug. We start simulating this program. Start here. Move A point 55H. A is equal to 55. Move P0A. 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 We can see from here. We cannot see this. Here, we need to add the 10 keys resistor to the P0 P0. So we need to stop this add resist resist 10 keys. Use the resist pack. We use this HV resist pack with comma. It's 7. Here's 10 keys. 10 keys. There is a VCC. So we connect one VCC. Now save this. Save this. Start the simulate. Move A 55H. Move A. Move P0 A. P0 A. This P0 is equal to A. Equal to A. Here is P0 equal to A. Equal to A. We can see this. Here, right point, right box, right box is high level. High level is equal to 1. The blue box, blue box is for the no level. No level is equal to 0. 0. So use is 1 0 1 0 1 0 1 0 1 0 1 0. Here move the 55 55H 55H. This is the binary for 55H, for 55H. So we can see the D0, the D0 is 1. The second is 0. Next is 0 1 0 1 0 1. So we can see from here. You can see 1 0 1 0 1 0 1 0. We can see the result from here, or we can see the result from here. From here, it's move A to move P0A. Next, move A 0AA 0AA. We can see ACC is AA. move P0AA 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 here P0AA 0AA we can see the AA 0101 0101 is A this is AA AA. This is we can see here. We can see from here. We can move to the digital to the port 0 to the port 0 in order to make port 0 as an input, we need to write 1 to the OR port, So like this program, write FF to the P0, so we can use it as input port, This is an example. Move FF and move P0 move P0 So write the 1 to P0 make the port used as input move P0 get the date from P0 from the P0 move P1 send it to P1 send it to P1 as example tell us if you want to use the port as input, we need to write 1 to all bits Port 0 is designated as AD0 AD7 AD0 address and date 0 address and date 7 and know it to be used for both address and dates when connecting an 8051 or 8031 and to an external memory, the port 0 provides both address and date. Port 1 can be used as input and output. In contrast to port 0, this port does not need any pull-up resistor. Since it already has pull-up resistor internally. Upon reset, port 1 is configured as an input. The following code will continuously send out to port 0 and altering the value 55H and AAH. This is a simple example. move A pound 55H 55H move PA move A to P1 output delay CPL converts the SJMP back SJMP back this is a loop this is a loop.
This, what does it mean, this CPL? I forget. Can you please say it again?
CPL gets the inverse of A
Okay.
yeah. To make port 1 an input port, it must be programmed as by writing 1 to all bits, just like this example, write the FF to the port 1. So this port 1 used as input, read move 1 so move P1A get the date from the P1 get the date from the P1, save it to R7 save it to R7 delay move save it to R5 this is a initial program for the use P1 P2 port 2 can be used as input or output just like P1 P2 does not need any pull-up resistor since it already has a pull-up resistor internally. Upon reset, port 2 is configured as an input port. From here, we start again. After we start this simulate, we can see P0, P2, P3, P1, all is high level. All is high level, which means write 1 to the port. So the port after reset, the port is configured as input. Upon the reset, P2 is configured as input. To make port 2 an input port, it must be programmed as such by writing 1 to all its bits. In many 8051 based systems, P2 is used as simple I/O. In 8031 based systems, P2 must be used along with P0 to provide the 16-bit address for the external memory. So we can see P2 is used as address 8 to address 15. P0 used as address A0 and A7. This is the same for the 8031 and 8051. 8031 and 8051. Port 3 can be used as input or output. Port 3 does not need any pull-up resistor. Is configured as an input port upon reset. This is not the way it is most commonly used. It is not the way it is mostly commonly used. So the port 3 has the alternate function. We use the alternate function for port 3. Here, port 3 alternate function. Port 3 has additional function for providing some extremely important signal. Extremely important. Port 3 0.0 and the point 1 0.0 and 0.1 used as a serial communication. Serial communication. Port 3.2 and port 0.3 used as external interrupt. External interrupt. Port 3.4 and 0.5 used as timer. Port 3.6 is a right signal. 0.7 read signal. So for port 3, the additional function, alternative function is important. Write a program for this microcontroller, touch all the bits of P0 and the P4 every of a second. This is a program. I simulated this for you. P0, A, P1, and always P1, A, and always P2, A. Delay. The 1, H3, and always and 4, and 2, 4, 8. H2 R3 and 255 H1 DJNZ R3 H1 DJNZ R4 H2 DJNZ R5 H3 RET. This is the program for the control the P0, P1, and P2. First four. First four. Second first four. Second is a delay. This subprogram delay I don't introduce. We see the main program. Move A pound 55H. Now A is equal to 55H. 55H here. 55H. Move P0A. P0A. We can see 55. We can see P0 here is 55. 55. Here P0. Move P1A. Move P1A. P1A. P1A 55. We can see P1 here 55. Move P2A. P2A here P2A. We can see P2 here is 55. So after that, we call a delay. After a call is finished, move A and 0AAH. And now A is equal to AA. So move AA to P0, P1, and P2. P1, P0, P2. You can see P0 is AA. It's AA. Next, the P1, P2 is 55. P1 is 55. We can continue the P1 change to AA. Change to AA. Next, PB is changed to AA. Here we can see PB is changed. Here is the example. We can output the data to the port. And in this program, we output the data from the A to port. Exactly, we can use the port directly, just move the data to the port, move the data to the port, like this. This use the two lines, we just use one lines, one lines. Sometimes we need to access only 1 or 2 bits of the port. Only 1 or 2 bits. We can use this. P1.1 access the set bit of P1. Set bit of P1. Set of the P1. We can see the is CPL P1 set B set B CPL get the inverse set B just set to 1 set to 1 CLR set to 0 set to 0 there's code I have already introduced in the instruction set. You need use how to know how to use this instruction. Important is how to access only 1 or 2 bits of the port. Use P1.1, P1.2, P1.2. P1 point 0 to 7 to access the bits of the port, access bits of port. Just the next here, this is port 0, D0, D1, D2, D7, D7. Here is an example. Write the following program. Create a square wave of 50% duty cycle on bit 0 of port 1. Port 1. The 50% duty cycle means that the on and the off states have the same length. Therefore, we took the P0 with a time delay in between each state. Towards P1, towards P1 with a time delay. So I give you an example on how to simulate this. HERE set B P1.0. Error code. Sorry. We need to leave the error code. just use the delay here. HERE. Set B P1.0 L call delay CLR P1.0 LCAL delay SGMP HERE. Let's see the result. Simulate. Before I simulate this program, I need to put a scope. Put the scope here. Scope. Alternate scope. P0 connected to the scope port A. So let's simulate this example. Debug. Firstly, I just ran this program. We can see here we can see the not a strictly square just we can see the neck square neck square we can see neck square. Start executed one line by line here. Set B P1.0 P1.0. So we can see after this is executed P1.0 set B set B is set B1 set B1. Next next delay delay. After the delay CLR P0 P1.0. Next the P 1.0 become to 0 become to 0 after the delay SJMP here jump back here. So set B P 1.0. You can see P 1.0 become to 1 become to 1 so you can simulate line by line. You can see the result from the oscillator scope yeah. This is an example for I/O ports. Okay. Let's have a break. Let's have a break.
Yes, Losh, yeah. But
Hello. Hello. Hello, everyone.
Hello,
Yeah.
Laoshi.
Let's continue.
Yes.
I have already simulated this program. You can after class you can do it by yourself. Do it by yourself.
Yes, Logic. Can you please share the PPT with us right now?
You cannot see the PPT.
Yeah.
Okay. I share it again.
Send us on WeChat group, Laoshi.
Now you can see the PPT. Can you see the PPT?
Laoshi, we can see, but I said, can you share the PPT with us?
Oh, you want me share this PPT in
Yeah.
WeChat?
Yeah.
Okay. After class, I give you the PPT.
Okay, but okay.
You want to see the PPT now?
Yes, Laoshi, if you can share it now, then it will
Okay.
be good.
I share you the PPT now.
Okay.
Now I have already shared the PPT in the WeChat. In the WeChat. This is the instruction used for this example. Used for the example. Set B, CLR, CPL, CPL.
Yeah,
This
Laoshi, you
is
got the PPT.
yeah, I have already shared PPT in the
Yeah,
WeChat.
Laoshi, you got it.
You got it?
Yeah.
Okay. This is a jump instruction. Jump instruction. These are instruction used for bit operation. Bit operation. Just for bit. JMB and JB instruction widely used single bit operation. Single bit operation. They allow you to monitor bits and make a decision depending on whether it's 0 or 1. These two instructions can be used for any bits of I/O port, any bit. Port 3 is typically not used for any I/O, either single bit or byte-wise. Mostly we don't use the port 3 as a common I/O. It's instruction for reading an input port. This is reading input. This is reading port. This is judge the bit. Judge the bit. This is judge the bit. This is move bit to C. Move the bit to C. Bit to C. 好。MOV A pound 45H again JMB P1.2 AGAIN move P0A set B P2.3 CLR P2.3 Okay, this is a program for this example. We can see the monitor. Symbol move. Oh, sorry. I read P0. I read it to PO. PO. Debug. Run line by line. Set B P1.2 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 here is high level, is high level. So if we execute this line, the P1.2 still high level, still high level. So move A pound 45H, 45H, 45H. So A is equal to 4545. Again, JMB P1.2. If P1.2 is zero, jump to again, jump to again. So after this execute, because the P1.2 is 1, so this loop cannot be processed, cannot be accessed. So move to next, so move move P08, P08, A is 45H, 45H. So after this is executed, P0 is 45. This is P0, P0. We can see the value here, 45, 45. 45, we can see for the 45 to the binary is 1000101, 1000101. So we can see 1000101 here. This is for the 1, 2, 3, 4, 5, 6, 7. 7 is 1. The 8, the 8th is 0, 0. So this is 0, 1, 0, 0, 0, 1, 0, 1, 0, 1. From this example, we can see how to control the bits, how to control the bits. So next set B P2.3, 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 P2.3 here already high level. So here is clear P2.3. After this is execute, we can see P2.3 is no never, no never. It is 0, is 0. So this here we can see how to operate on the bit, this is
Okay.
What? Sorry, I cannot hear you. I just give you this example for you. This example. This is a loop. It's a loop. So we can see the execute this example. JMB P 2.3 JMB is 0 just if it's 0 just loop here. But the P 2.3 P 2.3 is 1 is 1. So is go to the next it go to the next next P 1.5 set B CLR P15 SGMP back so this is a loop we can see the result we can see the result we connect the P1.5 P1.5 here stop the simulation 1.5 to here. We can see the ABC Here we can see the signal high, no, high, no, high, no, high, no. This is the status of P 1.5 P 1.5. If you want to simulate this program, you need to learn how to use this software. So I suggest you find some book about this software, or just read the help file. You can read the help file for your simulation and help you to learn how to use this software. This is another example. I hope you can simulate this program by yourself. Next, I introduce some about the reading input pins or port range. Reading a port, some instructions read the state of port pins. Others read the state of an internal port range. Therefore, when reading port, there are two possibilities. Reading the state of input pin, reading the internal range of output port. Confusing between them is a major source of the error of 8051 program, especially where external hardware is connected. Some instructions read the contents of an internal port range instead of reading the state of an external pins. For example, look at the ANL P1A instruction, and the sequence of action is executed as follows. First, read the internal range of port and brings that data into the CPU. Second, this data is ended with the contents of register A. The result is rewrite back to the port range. The port pin data is changed and now has the same value as port range. Read, modify, and write. This instruction read the port range normally, read a value, perform an operation, then rewrite it back to the port range. All these instructions read, modify, and write. If you execute this instruction, instruction will do read, modify, and write. The port in 8051 can be accessed by the read, modify, write technique. This feature saves many lines of code by combining in a single instruction, all three actions are all three actions. Now we end this PPT. I continue introduce the next PPT. Last class, I have already introduced the address model. And we just review this content. Just review this content. Because when we write a program, we need to know how to access the data. Access the data. So we just review this content. Addressing model is the main program, main content of this PPT. Immediately register direct, register indirect, and indexed. The source operand is a constant. We call the immediately address model. Immediately address model. If we put a pound before the value, this is just a date. This is a date, not an address. Not an address. So this source a pound is a content. Is content. The immediate data must be preceded by the pound sign. By the pound sign. As pound sign. Can load the information into any register, including 16-bit DPTR register. DPTR can also be accessed as 2-bit register, high bytes and no bytes, high bytes and no bytes. We can use EQU direct, directive to access the immediate data, count EQU30, which means if we want to use 30, we just use this symbol. Use this symbol. We can use immediately address model to send data to 8051 port, just like this one. Just like this one. Use register to hold the data to be manipulated. Use register to hold the data to be manipulated. This register. The source and the destination register must be matched in size. It's use the register addressing model. Register addressing model. Accessing memory. Use the direct addressing model. Direct addressing model. Just use the digital for the address. For the address. Just like this example. This example is move A4. 4 is the address. 4 is the address. This is a register address model. Register address model. There is no pound sign in the operand. If no pound sign, we know this constant is a address, not a data, not a data. SFR are registered and their address. SFR Special function register can be accessed by their names or by their address, by the address or by their names, by their names. Move this address with 55H, with this one is the same, because the the address of A is E0H, E0H. The SFR register have address between 80H and FH. Not all the address space of 80 to FF is used by SFR. The unused location are reserved, must not be used by the program, This is a special function register address. Normally, we use the symbol for this special register. Special register. We don't use the address. We don't use the address. This the symbol. This is the address. Here is some example. Write code to this is use the symbol. Use the symbol P1, P2. P1, P2. They use the address. Address. You can check this program by yourself. You can check this program by yourself. This is another program. Only direct addressing model is a node for pushing or popping the stack. This is special. Only direct addressing model is a node for pushing or popping the stack. Push A is invalid. So if you want to push the A, you need to use the address. You need to use the address. Use the address. Just let this example. A register is used as a pointer to the date. It's called register indirect address model. Only register 0 and 1 are used for this purpose. R2 to 7 cannot be used to herald this the address of an operand located in the RAM. When R0 and R1 hold the address of RAM locations, they must be preceded by the 8th sign. This is a register indirect addressing model. Here is some example for the register indirect addressing model. The advantage is that make accessing the data dynamical rather than statical, as in the direct address model. So register indirect, we can accessing data dynamical. Accessing data dynamical, because we can change the register with instruction with instruction, so we can change the address change the address Looping is not possible in direct address model. So if you want to make a loop, you need to use register indirect or some indirect some other indirect address model. Here is an example for register indirect. You can simulate by yourself. R0, R1 are the only register that can be used for points in register indirect address model. Since R0 and R1 are 8 bits wide, their use is limited to access any information in the internal RAM. Whether accessing external connected RAM or on-chip ROM, we need 16-bit points. 6-bit points. Mostly we use DPTR. Use the DPTR. Indexed addressing model is widely used in accessing data elements of lookup table. Indexed addressing. Accessing the data elements of lookup table. Located in the program ROM. The instruction used for the purpose is move C. This is different. Move C. Access the data in the ROM. External ROM. Move C. In the instruction used for this purpose use instruction move C. C means cause. C means cause. So this code is for ROM. The contents of A are added to the 16-bit register DPTR to form the 16-bit address of the needed data. A are added to the 16-bit register DPTR here. Form the 16-bit address of the needed So we can find the address with A plus add DPTR. Here is some example. This is an example. Now I want to give you some assignment. Anybody can hear me?
Yes, Laushi.
Yes, Laushi.
Oh, I thought maybe you were tired. You were tired.
Yeah, enough for today, Laushi.
Okay. So I give you some assignments. After you have some rest, I need you finish your assignment. You can select at least 3 example. Select 3 example from my PPT and simulate the example and write your simulate progress simulate process simulate process and explain the process in a Word file in a Word file, doc file, DOC files. Okay.
Okay, Lao Shi.
And after next I give you 1 week. Give you 1 week. I hope you can send the assignment with your
Mail ID?
doc files. Okay.
Sorry?
Send to me next week.
Okay, Lao Shi.
No problem.
No problem.
Okay.
Just give us
Everyone,
the your mail ID, Lao Shi.
什么
Your
you
mail
speak
ID.
Chinese?
Where we submit the assignment? On
Where?
WeChat or mail ID? Email ID.
If somebody they don't come here. I don't know how to get along with these people. They didn't come here. They come here. So after I finish this class, I give you the attendance list to the office. To the office, they decide how to do with these people. These people. So if you can hear me, I hope you
Lao Shi.
can finish it.
Lao Shi,
Lao Shi.
I want to know how can we send you the assignment on your
You
email?
can send me the assignment to the email. To the email.
Yeah.
I give you the email address. Give you an
Yeah.
email address.
Just send us on WeChat, Lao Shi, your mail ID.
No. If you send me by the WeChat, maybe I forgot the files. Forgot the files. You can send me to this address. This address. After you finish your assignment, you send your assignment to me. To this address. yjemail@qq.com. I hope you can write the subject.
Can you please
Subject.
write on WeChat?
What? I hope you write the subject.
信给你的邮件在微信吗？
Okay, you can add give the assignment to the WeChat, but I hope you can send me by the email because if
没问题了，你发你的 email 在我们的 group。
okay, I send
Okay,
the
okay.
email to your WeChat group. Okay.
Yes,
Okay.
Lao Shi. Yes, Lao Shi.
谢谢老师。
Okay. So much for today.
Yes, Lao Shi.
So much for today. Class is over.